The last type of spectroscopy that we'll examine is called NMR spectroscopy. Now we've already been introduced to NMR spectroscopy a little bit in chapter 2, and I'm going to kind of explore a little bit of the theory behind it and show you an actual spectrum and how what we can do with that spectrum in terms of analyzing it. Now, NMR spectroscopy measures the absorption of radio waves. So remember, spectroscopy is measuring the absorption of electromagnetic radiation. So in this particular case, we're looking at radio wave radiation. And what it corresponds to is what we call nuclear spin states. So remember that nuclei, just like electrons, have different spin states. And what happens is that this can tell us information about the carbon skeleton and the hydrogens attached to the skeleton. So remember, we talked about infrared spectroscopy and said it's very qualitative. NMR spectroscopy is a little bit more quantitative. And when we really get into NMR spectroscopy, which we will as the semester progresses, we'll see that qualitative nature coming out, so that in the end we can look at a spectrum or two spectra, and we can determine the structure of a molecule based on those spectra. Now, what's happening? The theory of NMR spectroscopy, and I'm not going to get into great detail about it, but in essence, here's a little pictorial that can hopefully get you thinking about what's happening in that spectrum. So if you look on the left-hand side, A, what we have is when we're looking at molecules, those molecules in the absence of an applied magnetic field are going to be randomly oriented relative to one another. Now, when you place a sample in a magnetic field, what happens is some of the nuclei are going to align with the field, and of course more of the nuclei are going to align with the field than align against it, because it's going to be at a lower energy. But some are going to be aligned against the field, and so we create these two energy states, alpha and beta. And depending on the size of the magnet, the separation between alpha and beta is going to vary. So the greater the magnet, the greater the separation. But they all fall within the range, and if you look at the difference in the energy between alpha and beta, that energy corresponds to energy provided by a radio frequency. So what happens is, here we now have our sample, now it's on the left-hand side, that is in a magnetic field. And we can pulse our sample with the radio wave that corresponds to that energy gap between alpha and beta. So now what happens? Well, now we've supplied enough energy for some of the nuclei in the alpha state to go into the beta state. So now we've overpopulated the beta state. But we've artificially done so, right? We've added energy to that state, but it's not in its natural ground state. So what happens? Once that pulse of radio frequency is completed, it's finished, and we're not supplying it anymore, then that sample is going to relax down into its original state, and it releases energy. And we can detect the energy that is released from that process. Now, one of the things that we have to recognize is that electrons also have spin, and they shield the nuclei from the magnetic field, making what we call the effective magnetic field less than the applied magnetic field. And so what happens is, you have a molecule, and that molecule has nuclei that are going to be affected by the magnet, but also each nucleus is surrounded by electrons. And those electrons are going to change the effective magnetic field of the nucleus. So changes in electronic environment will affect the magnetic strength, right? So that's kind of the key, the takeaway from this theory, that if I have nuclei that have different electronic environments, then each nucleus is going to have a different effective magnetic field. And because of this different effective magnetic field, it's going to have different radio frequencies that allow for that transition. So in reality, our instrument actually pulses at a variety of radio frequencies to account for that. And we can determine what those radio frequencies are. And so that's what we're measuring in the NMR spectrum. We're measuring those variations in radio frequency. So this is what a spectrum looks like of an NMR. This is a carbon-13 NMR. Notice the axis, the x-axis, goes from essentially 0 parts per million down to 180 parts per million in this particular spectrum. So the x-axis is expressed in parts per million. This is called the chemical shift, and we'll talk about that in just a little bit. But in essence, it is a way to normalize all the various different types of NMR spectrums that have different sizes of magnets, right? So if you look at this spectrum, and what I want you to take home from this spectrum is this is ethyl 2-butanoate. And if you look at the structure of ethyl 2-butanoate, you see that it has 6 different unique carbons in that structure, right? So we can label them 1, 2, 3, 4, 5, 6 and see that each one of these carbons is unique electronically. They all, there's no 2 carbons that are identical to one another in its environment. Now also notice that if you're looking at the spectrum, you see signals, and there are 6 of them. And if you look closely, you actually see 7, right? Well, if I label these from the left to right, A, B, C, and now I get to this, it looks like a darker signal, that actually is deuterated chloroform. So oftentimes we have to take into account the solvent that we use in preparing our sample. Oftentimes we're going to be using a deuterated chloroform, and we know that deuterated chloroform shows up at 77 parts per million in the C13 NMR spectrum. So we can say, okay, that's not part of the spectrum, but we have D, E, and F, and so A, B, C, D, E, F, those are our 6 signals that we would expect to see in this particular compound. Now the question is, well, can we go a step further, and can we pinpoint which signal corresponds to the appropriate carbon? And for many cases, we can do that. And the way that we can do that is by examining what's called the chemical shift. So what happens is electron withdrawing groups reduce the electron density at the nucleus. So remember, we have an applied magnetic field, and electrons around the nucleus shield that nucleus from the applied magnetic field, right? So they essentially decrease the effective magnetic field. But when you have a group attached to that nucleus, so say a carbon, when you have an electron withdrawing group from that carbon, now you have less electrons around the nucleus. So this increases the effective magnetic field, right? This effect, this withdrawing effect, increases the effective magnetic field. The result is now I have a greater effective magnetic field, and therefore it requires a higher frequency to resonate, to go from alpha to beta. This whole process we call de-shielding. right? Electron shield, now we have electron withdrawing groups that are creating a de-shielding effect. And we say that the chemical shift, right, or the shift in that resonance is downfield. So it shifts the resonance downfield. Now, oftentimes when we think of down, we think of, oh, okay, it's going to a lower number. No, it's actually going to a higher number. So downfield refers to, if you were looking at a spectrum, going to the left, going to the left-hand side of the spectrum. So this is a little bit counterintuitive and takes a little bit of getting used to. Downfield means going to a higher chemical shift, right? So this is what electron withdrawing groups do. They de-shield nuclei and they cause the resonance to be shifted downfield versus upfield, which would be to a lower chemical shift. So we have downfield, we have upfield. Downfield is to a higher chemical shift, upfield is to a lower chemical shift. Now, another effect that we see is the effect of pi bonds. Pi bonds also de-shield due to what we call an induced magnetic field in the pi bonds. So pi bonds actually have an induced magnetic field in which the electrons in that field actually add to the applied magnetic field. So instead of shielding, they're actually adding to the magnetic field, which again increases the frequency to a higher frequency. So again, you see a shift downfield. And that's important to understand. So we have electron withdrawing groups that de-shield, and we have pi bonds, in essence, that cause a de-shielding. So if I look at table 9.6, I can get an idea. This is common chemical shifts for the various types of carbon. So we're looking at carbon-13, the chemical shifts of carbon-13. And one thing that I want to note is the scale. So carbon-13 spectra typically fall between 0 and 220 parts per million. We're going to see that proton NMR has a little bit different scale. But the effects are the same, right? So the effects of de-shielding are essentially the same. If I look at alkanes, they have low chemical shifts, so they're upfield, basically from 0 to 40 parts per million. Whereas alkenes are shifted downfield, they have a higher chemical shift, between 80 and 145. Aromatics are about this in the same range because we have sp2 carbons. We have those pi bonds that are associated with it, and so we have that de-shielding effect. And so now notice on the right-hand side of our table, we have carbons that are attached to various electron withdrawing groups. So carbon attached to an oxygen is shifted downfield to between 50 and 90 relative to that of an alkane. Likewise, amines, carbon attached to a nitrogen, not quite as much of a chemical shift because the nitrogen is less electronegative. And you can really see that with the halogens, right? Fluorine is highly electronegative. It's going to withdraw electron density from a carbon the most, and therefore the chemical shift is going to be shifted downfield to between 70 and 80. Now, one thing to note is a carbon-oxygen double bond versus a single bond. There's a huge difference. A double bond withdraws a lot of electron density, and therefore the chemical shift is way down toward the end, toward the left-hand side of the spectrum, at around 190 to 220. So the table 9.5, which actually comes before 9.6, but oftentimes carbon is a little bit easier to explain than hydrogen. We're going to get into greater detail about proton NMR. There's lots more detail of proton NMR that we're not going to discuss at this moment. We'll get to it in the lab later on, and we may discuss it a little bit in lecture. But here is, again, a table of proton NMR, and you see that the range is a little bit different. The range for proton NMR spectra is between 0 and 12 parts per million. So the scale is a lot smaller, but the variations are still the same. You see alkanes showing up upfield, and you see, the more electron withdrawing group, shifting the hydrogens downfield. And that's really what I want you to take home at this stage. That when you have electron withdrawing groups, the greater the electron withdrawing group, the more it's going to shift that nucleus, be it a carbon-13 nucleus or a proton nucleus. So let's go back to the example of ethyl trans 2-butenoate. And let's see if we can, think about what carbons are going to have different chemical shifts and why. So again, if we number 1, 2, 3, 4, 5, 6, and we look at our spectrum, we see we have a signal down around 170, roughly 170 parts per million. So that is really downfield, and we should note that, if you remember, carbonyls are shifted way downfield, and therefore I can label that carbon number 4 in my spectrum. Then if I go a little bit to the right, a little further outfield, I have two peaks, one at 145 roughly, and one at roughly 120 parts per million. So these are going to correspond to my alkene carbons. Why? Because again, the pi bond is going to de-shield the nuclei from the magnetic field, right? So they're going to have higher frequencies than we would normally expect in an alkane. Now, one of the questions is, well, which one, so I have two carbons, both of them are different, which one is going to be shifted downfield, further downfield, and which is going to be shifted further upfield? In order to do that, we actually have to think about resonance, and we can draw a resonance structure which places the pi bond between the two carbons up to create a pi bond between the carbon and the carbonyl carbon, and then moving a pair of electrons up from the carbonyl to the oxygen. That places a negative charge on the oxygen, but it places a positive charge on carbon number 2. Remember, electron withdrawing groups. Well, if I have a carbon that has a positive charge, it is much more electron deficient than a carbon that doesn't have a positive charge. And therefore, I can say that carbon 2 is going to be the one that shifted further downfield, and carbon 3 is the one that's not shifted as much. Now, moving on, I see a peak at about 60 parts per million. What do I have left? I have two methyl groups and I have a methylene group. Now the methylene group, that CH2 group, notice, is connected to an oxygen. And if you look at the table, you see that carbons connected to oxygens have a chemical shift around 40 to 70 parts per million. So this I can label carbon number 5 with pretty good reliability. And so the last signals I have are of two methyl groups, 1 and 6. Can I say which one is 1 and which one is 6? Well, probably the one that's closer to 20 parts per million is going to be carbon number 6. Why do I say that? Because that oxygen connected to carbon number 5 is also going to withdraw a little bit of electron density from carbon number 6. Not to as great of an extent, but it will have a bigger effect than carbon number 1. So, I could probably make a case that carbon 6 is going to be shifted downfield. And therefore, I can essentially label every single signal with the corresponding carbon. And that's what we're going to be looking at throughout the semester. Can we get to a stage where, with relatively simple spectra, that we can, in essence, label each signal with the corresponding carbon or hydrogen?